Hi everybody, this is Dave Barrick. Let's take a look through the VPP engine infrastructure library, which is called vppinfra. The place I want to start is to walk around some of the header files and just try to give you a sense of what's there and to transition into a little bit of writing out some code snippets that you may find interesting. At any rate, the first thing to say is if you've cloned the OpenVPP repos into VPP, the header files for vppinfra will be found in vppinfra, and then star.h, where we might as well start with types.h, which is a really fairly simple thing with all the folder all stripped out. One ends up with definitions for signed and unsigned 8, 32, 16, and 64-bit integer types, named as we see here and walk through. We end up with unsigned and signed 8, 16, 32, and 64-bit integers. Floating point, float and double types effectively. There are also two types that are a little idiosyncratic to vppinfra, one called uword and the other called word, which is across multiple architectures is an unsigned integer as wide as a pointer or a signed integer as wide as a pointer. That it's worth looking at that, but you'll see that there's a certain amount of architecture if-deffing done in here, but suffice it to say that on x86 64, on ARch 64, on PowerPC 64, those are the types you'll end up with. Now if we look here again at my notes, vector.h, let's go look there. Also in vppinfra is an epic catalog of vector types where these are objects with attribute vector size sub n, where n is 8, 16, or at some point in the reasonably near future 32, you'd have to say. Reason this code doesn't especially depend on 256-bit AVX2 vectors yet is that there are an awful lot of Nehalem class CPUs floating around, and until we start leveraging some of the architecture-specific stuff in GCC 5+, which we will soon, it becomes difficult to have functions which are smart about, running the right version for the architecture. So we're going to get there, but at any rate, the vector types are up to 16 octets at this point in the game. And there's nothing real magic about this stuff. It's just a bunch of fairly ugly looking preprocessor magic. The other thing is, depending on whether one has SSE2, AltiVec, or the MMX unit, one ends up doing subsidiary includes of vector SSE2, vector AltiVec, or vector IWMMXT.h. So again, that's the vector header file. Cache.h is pretty straightforward. It's cache line size related definitions and prefetch definitions. Let's go take a quick look at it. And again, it has the obvious things. I mean, 64-byte cache line size for x86 64, a default size of 32 bytes, and macros to allow you to prefetch the appropriate number of cache lines to catch a certain number of octets. These macros work pretty well. When I get around to folding in the PowerPC and ARch 64 support, you'll see some additions here, but none of it's complicated. It's going to look pretty much exactly like this guy. The main variable one ends up setting is cliblog2 cache line bytes. Time.h are CPU clock tick definitions and a C structure wrapper. so that one ends up being able to maintain floating point seconds since the world booted. On x86-64, we have one ASM volatile, which does a read timestamp counter instruction. PowerPC 64, move from the time base. What's this one? Oh, who knows? SPU doesn't ring a bell. PowerPC 32, you'll notice the low and high time base registers being used, and a branch in case you got caught by the rollover to convert it to a 64-bit counter. ARM. This version ends up being deprecated. It's not immediately clear what the right solution for ARM is, in that there are multiple versions of what you use for a time base depending on the hardware. Again, on, and finally, if none of the above, throw up your hands and refuse to compile. There are in here, there's even a spin weight, although it would never be used in VPP code. Unix time now is done through a direct syscall wrapper to serve as a clock calibration. Let's see, Unix time now, nanoseconds. Yeah, pretty obvious stuff. At any rate, this this header file is about all of the CPU clock tick register support we ever need. clib.h contains a bunch of kind of miscellaneous macros of the form, how many bits are in a byte, what's the length of an array, some structure field offset macros, packed or unused attribute macros. It's a little questionable why these even exist, but then again, this code's been in use since 2000 approximately, so ours is not to question why sometime. The predict false and predict true macros are pretty obvious, build in expects. clib memory barrier, it's worth knowing, is async synchronized, that there are other forms of memory barriers available, but this one is the blunt sync synchronize. Init functions and exit functions are declared to be attribute constructor functions. We've seen that in the earlier talk in some detail as to how that scheme is used in the VPP engine, but here are some standalone macros and so on. The rest of the file is taken up with count leading and trailing zeros implementations, depending on whether the architecture happens to have assembly instruction support for it. Now I'd like to spend some real time on vec.h, which is the main vector or dynamic array package that's used throughout clib and really vlib, vnet, and the VPP engine as a whole. The next topic is really quite important, so we'll spend some time on it. Now, this comment right here describes the situation exactly. It says clib vectors are ubiquitous dynamically resized array with user-defined headers. Everything in the world is based on them. And what the memory layout of a vector looks like is the user gets a pointer to vector element 0. The vector has a certain length, which is in a minimal header, kind of back one set of octets. Vectors are canonically up to 4 gigabytes in count. That one can build the library with 8-byte, 8-byte contents, and as it turns out, even the memory allocator is vector-based, such that if you set the size of the vector length to an 8-byte integer, you can have heaps that are tens to hundreds of gigabytes. Don't normally bother with that. For typical data plane use, you just don't run out of memory, but it has been done to do in testing routing tables of tens of millions of routes rather than a few million routes. So at any rate, the take-home message is that the vectors are allocated objects that grow on demand. One thing to say is that a null pointer is a valid vector. It's just a vector of 0 length. You can always use the vec reset length macro on an existing vector or on a null pointer, frankly, to say, okay, we're not freeing the vector. That's what vec free does, but rather we're setting its effective length to 0. Now you might ask, why would you want to do that? And the typical answer is to recycle a vector over and over again without actually freeing it. That once the vector reaches some equilibrium size, you're not going to touch the memory allocator or ever copy it again. It's also quite reasonable to pre-allocate a vector where you know it's going to grow to a few hundred bytes, but you don't want to keep interrupting the parade with, oh, now I've got to stop and copy it and so on. It can, in some situations, be used as a poor man's substitute for a strategy where you don't hold on to dangly pointers. Taking the address of a vector element for any more than a brief moment is generally a mistake. A typical thing people do to hurt themselves is they'll allocate data in a vector and then go memorize pointers to the ith element. That's really bad. What you want to do is memorize I, because you can always get it back for a piece of simple arithmetic, maybe half a clock cycle, depending on how the microinstructions are actually issuing. But the last thing in the world you want to do is be memorizing pointers to the ith element of a vector and then expanding the vector. What ends up happening if you do that, particularly if you give such pointers to a hash table, is that all of a sudden the entire hash table starts acting sick, because the memory, the freed memory won't immediately be destroyed, but over a short period of time the thing will start working worse and worse, and eventually the wheels will completely fall off. Everybody makes this mistake once or twice, and then you learn there are a couple of coding patterns that you want to use. So in typical usage, let's say you wanted a U8 star junk. You could back add 1 of junk, comma 1. Okay, these are just adding, comma 2. You can do this sort of thing. You can then say if vec len of junk greater than 1, warning of more. You can do stuff like that. It's kind of actually worth doing that, and then to say, actually destroy the vector, just call vec free on it. Notice let's not do that mistake. There is actually a guy called vec add 2. I got too many 2's on my brain. But at any rate, vec add 2 is a little different than that, which is to say, if you were to say, let's say you had, struct, or better still, type def struct. If you were to do something like this, and you say junk t star jvac 0, and then you were to say vec add 2 of that basically means add one vector to the end of jvac and give me a pointer to it in jp pointing at jp pointing at value. or something. The point there is when you know you're pointing at a complex structure, rather than packing the thing up, the point is that rather than making a temporary instance of junk T, filling the fields out, and then doing a vec add 1, you can do vec add 2 to say, give me a pointer to, to an appended vector item, and then fill in the fields like that. It's just a much nicer way of doing it. So other things to say are the vec.h has doxygen tags in it, which explain, in some detail the arguments. In general, one thing I haven't talked about is that vectors are quite often aligned carefully. In other words, if you want an object or a vector of objects that's aligned to a cache line to begin with, it's quite easy to do that. Instead of vec add 1, you can do vec add 1 line of vec comma alignment, where alignment might often be clib. Alignment might often be clib cache line bytes. And that's a really fairly frequent pattern, and notice that it tends to port nicely across architectures. Now, across architectures where the cache line size actually differs, you may, when it comes time to do performance tuning, find that you have to adjust your data structure strategies a little bit, but at least you're not going to get completely crazy broken out of such things as that. Now, one thing I haven't talked about yet is that vectors can often have user headers. The point being, that one ends up, in the case where the header's present, you end up with the vector length, back an obvious distance from the user pointer, and the user header painted above that, aligned to a U-word boundary, whatever that is. Mostly 4 or 8 octets, 8 on x86-64. The point of having a user header is if you want to make a vector which is also something in addition, like for example to make a hash table out of a vector, or to make what's called a pool, which is an allocation arena, out of a vector, it ends up that you want fairly badly to have some ancillary data. For example, a pool is going to have a free list vector, a vector of indices corresponding to free items in the pool, and also a bitmap so that you can tell off the top of your head whether a particular item's free or not. And it's simple to make rather complex data structures out of the underlying vectors. It's a very nice, elegant little thing. The macros involved often come in multiple flavors, like if you say search for vec add 1. Okay, so here you go. Vec add 1 HA. We'll take a vector, an element. The header size in bytes needs to be supplied in each and every case, otherwise the underlying resize operator, which just thinks in terms of bytes, won't know what to do with it. And A is an alignment guy. Notice that the vector itself is a value result macro parameter. You can see from the form of it that it is in fact a value result macro. The point being, when you say vec add 1, there's no guarantee that v going in and v coming out are going to be the same. As I said before, they expand by 3/2 and shrink by 2/3 if you tell it to do that. The point being, don't sit on vector pointers. Just use the macros in the obvious way, and all will be well. The trouble comes when you make yourself 3 pointers to a vector and then expand it and fail to update a couple of them. Again, everybody makes that kind of mistake once or twice, but the fewer times you make it, the happier you're going to be. let's look at vec add 2. Okay, here we go. And again, it's the vector, a pointer to the new a pointer to the new elements. N is the number to add to the end of the array. H, header size, alignment, and both P and V are value result kinds of parameters. That P will definitely be set for you. It doesn't pay a lot of attention on it's actually set. Nobody pays any attention to what it was a minute ago, so it'll come back. If it had to expand the vector, you notice it's doing a vec resize. Vec resize, the underlying operator. The first thing it does is to see if it really needs to do anything, and because the vectors grow by significant jumps, if you're adding single octets to a UH star, it's not going to thrash the memory allocator each and every time around. Now let me show you vec. Let me not do that. Let me show you vec reset length. Oh, I predict that's in vec bootstrap. Vec reset length is pretty simple. If the vector's non-null, go ahead and set under vec under len, which if you look at the top of the screen is this guy called vec find, and vec find is going to be back up a little bit from the user pointer you got. Yeah, there you go. It's basically, here's the vector header. It's basically back up by one of the vec header guys. Now, as I was saying earlier, you can end up having 60. You can end up having very large vectors if you truly want them. Since CLib heaps are vectors, you can make a very large main heap this way if you want. We don't compile the code with CLib vec64 turned on, but really all you would have to do to make yourself a truly gargantuan heap is to compile with -d CLib vec64. You have to obviously compile everything in the planet because a variety of things will change in size, but it does turn out that the memory allocator and by implication everything else work properly with that. Of course, it's going to take an increasing amount of time to expand vectors when they grow to be the size of the known universe. So be a little careful what you wish for there. Now, to reinforce some of the things we've talked about, I've built up a really simple little test program which you'd be encouraged to actually go add to vppinfra yourselves and actually kick the tires. Simply put, we end up wanting these three header files so that the vector stuff and the types and so on are defined. And what this program is going to do is it's going to make a U32 star vector called foo, and we'll go ahead and add some elements to it. The reason for saying, after adding element I, foo is something or other is, as I've said, you can expect to see the vector periodically resize as we're growing it, and it grows by 3/2 roughly. So you can expect to see those numbers change a little bit. There's a little bit of doing veclen. There's deleting an element in the vector, which secretly is going to do a mem copy and then adjust veclen, and go through here and actually use vec reset length to leave the vector allocated, but make it effectively 0 elements in length. Add a single 1 to it, dump it again, throw it away, and show you what it ends up looking like. So the makefile.im change that I did is really obvious. I added this vexercise guy, and where did I put it? No inst. I added it temporarily to no inst programs here. I added these 3 lines. Let's get all the warnings known to mankind. There's where to find it, and add libvppinfra other libraries required to link against that guy. Now, just for fun, let's actually go touch makefile.am. If we go in here and we tell it metax compile, and we tell it to make from build root, platform equals VPP, tag equals VPP debug, vppinfra build, that'll actually just build the infra library, and by implication it'll go build this guy vexercise for us. So let's just go ahead and do that. And okay, that was dramatic. Did almost absolutely nothing. Any rate, now if we find ourselves a shell, we can actually run it. And if I'm clever, yep, there we go. Okay, so now let's look back at what it just said to us. And notice that the vector, when the vector was 1 long effectively, we were at mumble Charlie, mumble 70 for 2, 2C for a while, then 48, then C8. You can see that it's, reallocated it 1, 2, 3, 4 times to grow now to a size of 10. And I say without proof it won't grow again until it gets to be 16. After adding 10 elements, veclens 10. If you delete element 0 and then you look through it, you notice you get pretty much what you would have expected, which is the current vector element 0 has the value 1 in it, and so on. Now if we reset the vector length and add a single element, which is a 1, mumble, after freeing it, foo is now 0. So that's a useful exercise to actually go off and do and play around with the vector macros and functions a little bit yourselves. So here we have a bit more advanced exercise using the vppinfra. What I've tried to do in writing this test code is to produce something that's coded in the style of a data plane data structure lookup case, where you have fundamentally a key that the data plane is going to interrogate, and it's going to get back some data. In this case it'll be relatively trivial, but if you look through the existing codes, you'll see I've chosen to use the bounded index extensible hash templates and lookup mechanism, in that it's highly performant and also pretty worth seeing how to drive. There's nothing particularly complicated about it, but let's start oddly enough at the bottom of the file, where we say, okay, in this in this world we have to produce, because this is a test program, we're just going to produce a simple main. My main init is the sort of thing that you'd ordinarily execute via a vlib init function call, and in this specific instance, we have to set up the clib main heap just to give the test program, a little bit of a vector heap. At any rate, the remainder of it is actually fairly realistic. That we're going to say get a pointer to the session by session key hash and actually create it, much as you would in a real case. Now, one thing to notice about the bounded index extensible hash code is that it uses some name templating, because you can easily imagine a case where you've got more than one of these key geometries or key value pair geometries going on. There are a couple of them implemented at the moment that if we look at vppinfra, this is the key value pair format we're going to use, which is to say an 8-octet key and an 8-octet value. Look at these guys. Again, there's a little bit of controls and templating done here. That the bi hash type is a suffix that'll be pasted on to names by some of the templating macros. KVP per page is the number of key value pairs that we find in a single backing store instance. If you think about it, you end up with for the 8.8 flavor, we'll end up with 16 times 4, or surprisingly enough, 64 octets, which exactly will fill a cache line. So what we're saying is when we allocate the backing store for the bounded index extensible hash pages, we're going to end up with one cache line, per chunk. If you don't know about bounded index extensible hashing, it's kind of a cute deal where the lookup time remains constant. In fact, as we walk through not this file but the actual lookup template, it'll become fairly clear what's going on with it. At any rate, so the under 8.8 variant has a 64-byte key, a 64-bit key, and a 64-bit value. We have a certain small number of functions which say, tell me if this entry in the in the page in the backing store is actually free. clibxx hash is effectively Google XX hash, which is a fast, quick, easy way of hashing 8 octets with some pretty good statistics. There's a formatter which will say, the key's X, the value's back. A key compare, real simple, just, an equality test. Now the 24.8 variant, a 24 octet key, has actually, begins to use the vector unit for key comparison. At any rate, so back to the test program. So what you do is you say BVT, the macro. Well, let's go look at that for a second. Okay, let's go look at that for a second. You'll see what it's doing is it's doing, some type cut and paste where what you end up is transforming, clib bi hash value into clib b hash value under 8 under t for the instance we're doing. But at any rate, the macros are fairly simple to use. It's not C++, there's not real template classes, so this is kind of where you're left with. There's nothing inherently horribly wrong with spelling the type names out completely, although for purposes of this example I don't do that. So at any rate, what we're going to do is initialize stuff, initialize the hash table. This flavor hash table takes an object to initialize, a name for it, the number of buckets you want, and the size of the private heap you want. The algorithm here will split buckets by powers of 2, so it's not super critical to get the number of buckets right, although if you expect a lot of failing searches, you're better off to overpopulate the bucket array so that you won't end up having to pressure the load store unit as much to go find out that, oh, by the way, such and such doesn't happen. The other thing is, if you grossly missize the bucket array, you'll end up with a certain amount of wasted space. Again, it's not super critical, but you don't want to have 4 buckets if you're expecting 1 million entries. Yes, it's likely to work, but yes, it's going to waste a tremendous amount of memory in doing so. And in any event, you're going to get constant lookup speed. It's just a matter of how space efficient or space inefficient the thing is. You don't, by the way, want too many buckets because, as you've seen with the 8.8 key value pairs, there are 4 of them per cache line, and you'd like the cache lines to be relatively full. So you don't end up wasting your entire life, pulling in a cache line you don't really need to look through. So, or put another way, to really allocate more cache lines than you need. So at any rate, what we do is we do this main init thing, and then we go into the test UI. The test UI is itself a fairly interesting demonstration of how to use unformat, init string, and unformat. So the UI is pretty simple. It'll say add this key cookie pair, where cookie to the data plane would really mean the thing that you want to look up based on packet data. You have an add, a del, a find, a dump verbose operator, which will dump the table in excruciating detail, and a dump operator that'll dump it in a little bit less detail. Again, you're seeing unformat, you're seeing format. Format of standard out effectively does an underlying format operator and paste the results onto standard out. Also, the %u guy, which is to say, what we want to do is to call format bi hash, and in this case, under 8 under 8. And dump the the session by session key bounded index hash table. And the implementation functions are actually pretty simple. To search one of these guys, you get yourself a pointer to the hash table. You set the KV as in. You'll remember when we were looking at the definition of that particular flavor, you had an 8-octet key and an 8-octet value, and the story here is bi hash search is a straightforward search of that hash table for the input key value, or really key, and it'll return you in potentially the same variable, although ordinary for clarity one might do the KV return guy. And if it finds the key, you'll see the thing, you'll see the value you suggested. Otherwise, it'll complain that you didn't find it. Now, notice that in this case, I'm using CLib error returns, which are somewhat of a CLib or vppinfra idiosyncratic data structure. You'll see in the UI that if the guy returns one of these supposed errors, it'll just announce it. Well, if it turns out that that quote-unquote error happens to be I found the key with a certain cookie, off you go. So that's the find operator. The delete and delete and add operators are pretty obvious. The point with adding is you're best off to not add values that already exist, and it'll go ahead and do what amounts to a quick find, and then add the item. So what does this look like when running? Let's just actually metax GDB it. Metax good GDB. We'll run it up in GDB. Actually, I've already run it up in GDB, and you'll see it says command. So if we were to say key 11 cookie 1 2 3 4, and then dump verbose, you'll see there we go. In bucket 0, the 0th key value pair has the guy you were looking for, and if we actually asked to search it, we'll say find key 11, and there you go. Find key 12, not so much. Del key 11. Okay, now if we say find key 11, you'd be a little surprised if it found it, not so much. Add key 12. Whatever. Cookie. Whatever. Oh. Yeah, and that's what happens when you don't quite type carefully. So there you go, dump verbose, and we can see what we have here is we have values spread across 2 different buckets, not hugely surprising. Now, again, let's just quit out of here and look for a moment look for a moment at the search predicate. This will explain a bit about how the underlying algorithm actually works. bi hash. And what this guy does is it's going to say, okay, compute the per data type key hash based on the search key we've been fed, and find the find the bucket index. Yeah, it's pretty obvious that the number of buckets better be a power of 2. If it turns out that that the bucket offset is 0, meaning it's not been set, that's the end of the game. The search fails. Otherwise, you say throw away the bits you used to find the bucket, and then take log2 number of pages minus 1 more bits out of the hash code and add it to the value index. What this means is that that the actual bucket grows by powers of 2, and you don't end up having to do a linear scan. That the algorithm deals the key value pairs out into a larger space. I mean, you start off with one backing page, and then you end up with 2, 4, 8, blah blah blah. The point there is that there's a bunch of complexity which you can look at in the add delete code in BI hash template to handle the case where you end up having to split the buckets. But the code's pretty well worked out. At any rate, so here we do the data type specific key compare function and say, oh yeah, well, if it turns out that if it turns out we found the thing really in a single cache line misses worth of probing around, we'll get you back the value. In actual use of this technology, it's a good idea to split the lookup across some of the inlines that are made available, so that you can prefetch the bucket and go on to other work, then prefetch the single backing store page you have to search, go on to other work, and then come back and finally actually do the search. This is kind of the beauty of the method. The other thing that's worth knowing about is working. This make working copy guy, if you look through and get into the code more, you'll see that the code is set up so that readers are not synchronized against the single writer, which is synchronized against all other writers. That what we do in the writer is we'll make a temporary working copy of the bucket we're about to hack on, and let the world continue to look up using that copy. Then with a single 64-bit write, which effectively is atomic on x86-64, we'll snap our fingers and change the data that everybody's looking at. That turns out to be sufficient to let the data structure be pretty bloody thread safe. So it's an interesting data structure, and this sort of hash exercise that I've thrown together here is absolutely worth taking a look at in detail. That should give you a reasonable idea of how to drive a fair amount of the VPP infra routines that you're likely to run into in data plane coding. Again, there's a lot in VPP infra. There's a simulated annealing drive or whatever, but you might want to plan to just look around in the directory carefully.